Imagine you have a long story written in a secret code. The first job of the compiler is to chop that story into understandable words, just like a child learns to separate letters into words when reading a book. This step is called lexical analysis. Regular expressions are like simple search and replace patterns. They tell the compiler what a number looks like, for example, one or more digits, or what an identifier looks like, for example, a letter followed by letters or digits. The compiler builds a tiny machine called an NFA, which stands for Non-Deterministic Finite Automaton, that can walk through the characters and guess many possible paths at once. Then it converts the NFA into a DFA, Deterministic Finite Automaton, which has exactly one path for each character, like a well-trained robot that never hesitates. The conversion uses the subset construction algorithm, where each DFA state represents a set of NFA states. As the DFA scans the source, each time it reaches an accepting state it says "I found a token" and creates a token, for example number 42, identifier X+. All tokens are placed into a token stream, a neat line of Lego bricks that the later phases will stack together. Mathematically, a DFA is a 5-tuple of Q, sigma, delta, Q sub 0, and F, where Q is a set of states, sigma is the alphabet characters, delta maps a state and a character to a new state, Q sub 0 is the start state, and F is the set of accepting states. After the words tokens are ready, the compiler needs to check if they are put together in a sensible way, just like checking if the Lego bricks follow a building manual. This is syntax analysis or parsing. The rules for correct arrangement are written as a context-free grammar, or CFG. A CFG has productions like expr goes to expr plus term or term, which says an expression can be another expression plus a term, or just a term. Using the grammar, the parser builds a parse tree or abstract syntax tree. Imagine a family tree. The root is the whole program, its children are statements, their children are expressions, and so on. There are two popular deterministic parsing algorithms. LL1 reads the input left to right, produces a leftmost derivation, and looks ahead only one token, the one. It uses a parsing table built from first and follow sets. For each non-terminal and look-ahead token, the table tells which production to use. LR1 also reads left to right but builds a rightmost derivation in reverse. It uses a stack of states and a canonical collection of LR1 items. Each item looks like A goes to alpha.beta, A, meaning we have seen alpha, expect beta, and A is the look-ahead token. The algorithm shifts tokens onto the stack or reduces them using productions. Both methods guarantee that if the source follows the grammar, the parser will not get confused, like a GPS that never loses the road. Mathematically, a context-free grammar is a 4-tuple, V sigma, RS, where V is a set of variables, non-terminals, sigma is terminals, R is production rules, and S is the start symbol. Parsing gives us a tree, but the tree does not yet know what the words actually mean. Semantic analysis adds meaning just like a teacher explaining each word in a story. Attribute grammars attach extra information, attributes to the nodes of the parse tree. For example, a synthesized attribute type can be computed from the children. If a node is add expr1 expr2, its type is int only if both children have type int. Type checking uses these attributes to verify that operations are legal. You cannot add a number to a word, just like you cannot add apples to oranges without converting them. The compiler reports an error if a mismatch is found. The compiler keeps a symbol table, a big phone book that maps each identifier variable name function name to its properties, where it was declared, its type, scope level, and memory location. When the parser sees a use of X, it looks up X in the symbol table to know what X refers to. Mathematically, an attribute grammar is defined by a set of semantic rules R of the form, a.I equals f of b.jc.k, where a.I is an attribute of node A, and the function f computes its value from attributes of sibling or child nodes. The result of this phase is a semantically checked enriched tree ready for the next steps. Now the compiler turns the rich tree into a simpler almost machine language called intermediate representation. Think of it as translating a story into a series of short, clear instructions that any builder can follow. 3 address code TAC is a common intermediate representation where each instruction has at most 3 operands. For example, T1 equals a plus B, T2 equals T1 times C. It resembles a recipe. Take A and B, mix them, store in T1. Then multiply T1 by C store in T2. From 3 address code, we can draw a control flow graph, CFG. Each node is a basic block, a straight line sequence of 3 address code without jumps, and edges show possible jumps like if or while. The control flow graph looks like a map of roads showing where the program can travel. Static Single Assignment Form, SSA, is a special way to write 3 address code where every variable is assigned exactly once. If a variable needs a new value, we create a new version, x1 equals 5, x2 equals x1 plus 3. Static single assignment makes data dependencies crystal clear, like labeling each brick with a unique number so you can trace where it came from. Mathematically, a control flow graph is a directed graph, G equals open parenthesis B comma E close parenthesis, where B is the set of basic blocks, and E is the set of edges representing possible control transfers. The intermediate representation is the playground where most optimizations happen. With the IR ready, the compiler tries to make the program run faster or use less memory. This is optimization. Imagine cleaning a messy room. You put similar items together, throw away junk, and arrange things for easy reach. Data flow equations describe how information like is a variable constant question moves through the CFG. For each block we compute IN of B and OUT of B using equations such as OUT of B equals GEN of B union IN of B minus KILL of B. Solving these equations, often with a fixed point iteration, tells us where optimizations are safe. Constant propagation uses the data flow results to replace variables that always have the same value with that value. If we know x equals 4 everywhere in a loop, we replace x by 4, just like swapping a toy with a picture of the toy. Loop transformation techniques reshape loops for speed. Loop invariant code motion moves calculations that give the same result each iteration out of the loop, like packing snacks before a long road trip instead of every mile. Strength reduction replaces expensive operations such as multiplication with cheaper ones such as addition. I equals I plus 4 can become I equals I plus 1. Repeat 4 times if that is faster on the hardware. Unrolling repeats the loop body several times to reduce the overhead of checking the loop condition, similar to walking several steps at once instead of one step at a time. These optimizations are expressed mathematically using lattice theory and fixed point algorithms, but the intuition is the same as cleaning and reorganizing a room for efficiency. After optimization, the compiler must turn the IR into real machine instructions. This is code generation. Think of it as giving a builder a precise blueprint with exact measurements and tool choices. Instruction selection picks the best machine instruction for each IR operation. If the IR says T equals a plus B, the selector looks for an add instruction that matches the operand types and registers. Pattern matching techniques, tree matching or D/G matching are used, similar to fitting puzzle pieces. Register allocation decides which temporary values live in the few fast registers of the CPU. The classic model is graph coloring. Each variable is a node. An edge connects 2 variables whose lifetimes overlap. We try to assign a color register to each node so that no adjacent nodes share the same color. When we run out of colors, we spill some values to memory, like putting toys in a box when the shelf is full. Instruction scheduling reorders the selected instructions to avoid CPU stalls and make good use of pipelines. It respects dependencies. You cannot use a result before it is computed, but it tries to fill idle cycles, much like arranging a dance so that no dancer waits unnecessarily. Mathematically, register allocation can be framed as solving a coloring problem on an interference graph G equals V and E, where the size of V is the number of temporaries, and E indicates overlapping live ranges. The output is a sequence of binary instructions ready to be loaded into memory. When the program finally runs, the computer needs a place to keep track of what is happening. This is the runtime support layer. Imagine a theater, the stage which is the stack, the backstage which is the heap, and the scripts which are the calling conventions all work together. Stack frame layout. Each function call creates a frame on the call stack that stores local variables, saved registers, and a return address. The layout is like a stack of trays. The top tray holds the newest call, and when the call finishes, the tray is removed. Calling conventions define how arguments are passed in registers or on the stack, who cleans up the stack, and which registers must be saved by the caller or the callee. This is an agreed-upon handshake so that 2 functions can talk without stepping on each other's toes. Memory management deals with the heap where objects that live beyond a single function call are stored. Heap allocation finds a free block of memory, like finding an empty box, and garbage collection periodically scans for boxes that are no longer reachable and recycles them. Simple algorithms include reference counting, where each object tracks how many pointers refer to it, and mark and sweep, which marks all reachable objects then sweeps away the rest. Together, these mechanisms let the generated code execute safely and efficiently, just as a well-organized theater ensures every actor knows where to stand and when they speak.